In this lesson, we are going to be analyzing simple harmonic motion using the reference circle. So we'll call this analyzing simple harmonic motion using the reference circle. All right, so what we're going to do is we'll start off by comparing, observing. So observe relationship between SHM and uniform circular motion. And having done that, we'll be able to then use phasors and the reference circle to analyze simple harmonic motion. And finally, in the process of doing that, we will define, we're going to define angular frequency and relate it to the definition of simple harmonic motion, which, remember, in fact, I've even got those notes here. So remember, we defined simple harmonic motion as A is equal to some negative constant times x. So we're just going to make a statement about that constant at some stage as well. Okay. All right, so to start off with, what we'll do is we'll have a look at what we're talking about here. So here's a simulation or an animation of an object that's going to move in a circle at a constant speed, and next to it we have an object that's going to undergo simple harmonic motion vertically. So we can see that the green ball and the red mass remain aligned vertically throughout the motion. Even though the green ball is moving at a constant speed, its vertical position is not changing constantly. It's changing so that it's exactly in line with the red mass at all times. So relating these two, we will be able to analyze in more detail exactly what's going on with the red mass. We can see now that it's turned on its side, that the green mass is really, if we're looking only at the vertical motion, it's really carrying out the same motion as the red mass. Okay, so what we'll do is we'll start off by just sketching that relationship out. So I'm going to zoom in a bit more, and I'm going to draw myself a reference circle here. I didn't like that circle. Let me try that again. Okay, there we go, and I'm just going to resize it so it's in line with the lines a little bit better. Okay, and then just move it into place. That's good enough. Okay, then what we'll do is we'll draw the mass at 5 different positions. So we'll draw it at the starting point. So it's starting off moving through equilibrium heading upwards. And then at a later time it is at its maximum position. At a later time it's moving down through equilibrium. And then it is at its lowest position. Oops. And then it is back up at its starting position and moving upwards. Okay, and we can draw in the spring here as well, just so we know what we're looking at. And here the spring is really compressed, and here we have the spring stretched out again, and here we have the spring really stretched out because it's at its lowest position, and then here it's sort of stretched out again. Okay, so this is time equals 0. This is time equals 1/4 period. Let's get rid of that triangle. And this is after half a period. And this is 3/4 of a period. Whoops, that should be a lowercase t. And here we have now had a whole circle happen. So for our phasor diagram here, what we could do is draw the position of the object moving in a circle at all those points. So this is at time equals 0. This is at time equals t over 4. And then this is at time equals t over 2. And this is the position at time equals 3/4 of a period, 3t over 4. And then it's back around here at t equals capital T, and then it repeats the process. Okay, so when we represent the oscillator in circular motion, what we do is we represent it as a phasor, which is an arrow with the tip at the position of this red dot. So it's going to start off at this position, and it's going to move anti-clockwise, and it's going to complete a whole circle in a time big T, and it's going to move at a constant angular speed as it spins around here. Okay, so what we'll do now is we'll just take this picture here, so this circle, and we will analyze what's going on with the phasor in a little bit more detail. So I'll pop that here, and I'm just going to make it a bit bigger so we can see what's going on. Okay, so there's our phasor diagram. In fact, I want the center to be sort of centered on the grid here. About there. Okay, so if we look at the phasor at its starting point here, so if we have a motion where the object is moving up through equilibrium, then we can draw our starting phasor like that. And let's say we want to find out where it's going to be at a particular time. Well, the first thing we can do is we can figure out how quickly the phasor is going to be moving. So we're going to do that using an angular speed. So the angular speed of the phasor well, we know that omega is equal to delta theta over delta t. And we know that this phasor is going to complete 2 pi radians, so a full circle, in one time period. So the angular speed is 2 pi over t. So we can now, this is what we're going to define as the angular frequency of the simple harmonic motion. So define angular frequency. It's just the angular speed of the phasor. Omega is equal to 2 pi over the period, which is the same thing as 2 pi times the frequency, because frequency is just 1 over t, and so we can replace 1 over t with f. So this is an important definition, so this is worth highlighting in our notes. Okay, so now we know that this phasor is spinning with an angular speed of omega. And what we can do then is at a particular time t, so at a particular time t, the phasor will have spun through an angle omega times t. So if we draw in, let's say at time t, the phasor is here. This angle then will be omega t, and we know that the length of the phasor is going to be equal to the amplitude. I might not have made that clear up here. I'm just going to go back up here. So the highest position here this distance here, has got to be equal to the amplitude here for them to be in line. So the length of the phasor, we just add a note to this. I'll add it in green. The length of the phasor is the amplitude of simple harmonic motion. Okay, so we can label that into our bigger diagram here, that this length here is A, that length there is A, and its current position, x, so its displacement from equilibrium, that's just the distance between the tip of the arrow and the horizontal line going through the middle of our phasor diagram. So this distance here is x. So now we can write an equation for x in terms of the amplitude and the time that's passed. So we have the opposite side of the triangle here, and the hypotenuse here, so we're going to use O and H, that's sine. So we can say sine of omega t is equal to opposite over hypotenuse, x over a. So the position of this particular simple harmonic motion, x is equal to a times sine of omega t. Okay, so now we have an equation here where if we know a and we know the period, so we know omega, and then we can specify exactly where the object, the mass, will be in terms of how far it is from equilibrium at any time t. Okay, so that's how the phasor diagram works. There are some subtleties to using it, and I will go over some examples in the next lesson. But I will do one example here. So, example. So, we can say a mass spring system oscillates in simple harmonic motion with amplitude of, let's say, 0.50 meters and period t equals 2.0 seconds. At time equals 0, it is moving upwards through equilibrium. Where will it be? 0.3 seconds later. Okay, so the way to solve this is to draw a reference circle and then to draw in the starting phasor, which looks like that. And if the period is 2 seconds, then it's going to take half a second to get to there, 1 second to get to there, 1.5 seconds to get to there, and 2 seconds to get back to its starting point. So the phasor that we're interested in is going to be somewhere between the starting point and the vertically upwards. So I'm going to draw in that phasor there. I don't know exactly where it's going to be, but I'm going to draw it just so I can draw a clear diagram. And then I will label the angle here. That's going to be omega t. I'll just zoom in a bit to make this a bit clearer. Omega t. And the side that we're interested in finding is this one. This side here is going to be x. And we know that the length of the phasor is a. So now we have a right triangle here, which we can use our trigonometry to figure out. So we can say that x is going to be equal to a times sine of omega t, where a was equal to 0.5 meters, and omega is going to be equal to 2 pi over t, which is 2 pi over 2, which was our time period, which is just pi, and t was 0.30 seconds. So now we'll just plug those numbers in. So we get x here. This x is going to be equal to the amplitude, 0.50, times sine of omega t, so that's 0.3 times pi. And it's important that we keep working in radians. You can do all of this in degrees, but it will be easier if we work in radians now, because we're going to need to later. Okay, so let's work this out. So we had 0.5 times, and then we had 0.3 times pi, and this calculator only lets me do the trig function afterwards, so that's why I've done it in that order. And then we'll do sine, and we get 0.8, and we end up with 0.4045 for our displacement. So x is going to be equal to 0.4, what was it? 0.4045. So now we have a means to predict exactly where the oscillator is going to be at any time. There are some subtleties to using this, and so I will go over a series of examples in the next little video.